following on from our previous lecture, so we have now the types of machine learning. So we have actually currently four types of learning. So the first two are the two that was they were the oldest and one of the most established. So the first one is the supervised machine learning. So it's the simplest, relatively simple type of machine learning, and this one is usually used for classification of data and prediction of outcome. So how do you do a supervised machine learning? So in a supervised machine learning, your training set, basically your data here, are labeled. So it's just like you're giving the students. So for example, if you're the teacher and you're training your students, you're giving them both the test questions and the answers to the test. So basically, the machine will now know, or basically, this is used in predictive because the next time that, for example, based on your training data, so if this machine or this data is A, so this is letter A. If this data is B, this is letter B. Now, the next time that it encounters a new data that is not from the training set, it can, using the pattern it observed from the previous label data, it can then predict what the data is. So for example, so if you feed it pictures of bicycles, whereas you have two wheels with the handles, a very light frame, so you label it as a bicycle. So the next time that the machine encounters an image that has two wheels, a light frame, we have handlebars, it will know immediately that this is your bicycle. So basically, that's your supervised machine learning. So for the next, we have several algorithms for supervised machine learning. So we have the k nearest neighbors, we have the linear regression, and the logistic regression. We also have the support vector machines, decision trees, and random forests, and neural network. So we will be discussing these algorithms in the next week, and we will try a simple algorithm for that. Okay, and then we have the unsupervised machine learning. So for the unsupervised machine learning, this is unlabeled data. So they are, if going by the same analogy with the student giving exams. So in the supervised machine learning, you are given both the questions and the answers together with the questions. Okay, so you already know, given that question, you already know the right answer. Basically, the machine will just have to memorize the data from that question and given answer. Now, in the unsupervised machine learning, the computer, basically the student, are being given questions without answers, and they are never given the answers. So basically, it's up to the student, or rather to the machine, to find hidden patterns in the data. So basically, this is usually used if there are really no labels, no known answers, or no known labels for the data. So examples of data that are being used for unsupervised machine learning are gene expression data. So we have thousands of genes being analyzed simultaneously in gene expression data. So you have microarray or RNA-seq. So you have thousands of them. We do not know, because in the gene expression data, we want to know what genes are expressed, overexpressed, or under, what genes are being expressed too much or not being expressed too much under a certain set of conditions. For example, in a cancer patient, this gene or this group of genes are overexpressed because they are involved in the pathology of the disease. They are involved in the disease. And so in this set, with even the researchers do not know what the labels are. Whether that the labels here being the genes that are overexpressed or underexpressed, it's up to the machine to actually know, or rather find the pattern in this data. Another example here, for example, COVID. The instances of COVID patients where some people are symptomatic, some people are asymptomatic. We do not know why that happens, why some people are asymptomatic, and then his sibling or his sister or even his neighbor have severe cases of COVID. So that is an unknown, but we can gather the information from those sample individual. We can feed them to machine, and then the machine can perhaps find underlying patterns that maybe or well, optimistically, they can find reasons why this person got sick, why this person doesn't get sick. And also from that pattern, the next you can also make prediction. So this person, if it will have COVID, based on our previous data, he or she will have asymptomatic, we will have the asymptomatic version. So basically that's an idea for the unsupervised machine learning. So this is a more complex algorithm, unlike the supervised machine learning. Now we have several unsupervised learning algorithms here. So you have for the clustering type of algorithm, you have the k-means and the density-based spatial clustering of applications with noise. So basically, this is some of this we already discussed about feature extraction and sorry for the noise. Some of this we already had discussed in the last module about data cleaning and preprocessing. So as a clustering method. So another example is the anomaly or novelty detection. It's either a one-class single vector machine or an isolation forest. It can also be a visualization and dimensionality reduction. So you have PCA, kernel PCA. PCA that is actually we had already discussed this one a while ago. In the last module. So anyway, PCA, kernel PCA, sorry for the noise, locally linear embedding, distributed stochastic neighboring embedding. And then for association rules, we have a priori and ECLAT. So these are, basically ECLAT is, it's not actually an actual name, it's an acronym, okay? So anyway, those are some examples of the unsupervised learning algorithms. And they are actually the more complex versions of algorithms. And then we have a semi-supervised machine learning. So it's a combination of both supervised and unsupervised. This usually happens if you have a very large amount of data and it's a pain to actually label each one of them. So you have a large amount of data which are unlabeled, but in this case, you first gonna cluster this unlabeled data using unsupervised machine learning, and then give labels to the clusters, to the classifications. So given that, we can now feed it to a supervised, or rather we can now apply the supervised machine learning based on the labeled representatives of the clusters. So basically, this is your supervised machine learning, semi-supervised. So let's have an example for a semi-supervised. For example, in Facebook, the face recognition software in Facebook. So the face recognition software first identifies similar faces. So it will identify your face in your albums. You have many photos. It's a pain in the ass to actually label each of them. So you can have the photo recognition will first classify the similar faces. So you will identify a faces of each person, and then it will ask you, who is this, or is this, so on and so forth. So you as the user, you will then label them by telling, this is my cousin, this is me, this is my mother. So from that, the next time, so all the faces that matches your description of mother will be known as, basically your mother. So it will be labeled as your mother. So basically that is the semi-supervised machine learning. And then the last one is the reinforced machine learning. This is just emerging, a relatively new one. So in reinforced machine learning, you have the agent. Basically, this is your machine. So, the AI or the robot. So, uh you will subject, basically it's just how you do it again in a class. You subject, or how people learn, basically you subject it first to a question. This is how people learn in real life. So you subject it first with a question, and it will make a guess, a random guess. Well, if it's a relatively new question, it will make a random guess. So based on the answer, for example, this person here, the agent, given a choice between water and fire, so it it chose the fire. So of course it's hot, so ouch. So it's hurt by the fire, so there is a certain punishment for a wrong answer and a certain reward for a correct answer. So in the next time that you encounter, or your agent encounters that similar, same or very similar question, based on the punishment and rewards that you have, the agent will now be able to make the correct decision. So the reinforcement is being continuously updated, because as they encounter a new one, so they have a rewards and a punishment. So basically it's basically a continuous improvement type of system. It's like basically training your pet dog. So you give it a reward, it does a good thing. You give it punishment, hopefully not so much, not so bad punishment if it doesn't really comply. So basically that's your reinforced machine learning. Now aside from these four types of machine learning, basically this is how these types tells you or classifies the machine learning algorithms based on how you teach your machine. But aside from that, there are also several other characteristics of other classifications of machine learning. You have the batch and the online learning. So this is based on how on when, or basically your teaching method, or rather not exactly the teaching method, the number of times you teach your machine. So for example, in the batch learning, the system is incapable of learning incrementally. That means you give all of the data, all of the training data in one go. And after that, the system will develop a model. So now in the future, if that model is flawed or there are problems with the model, you cannot actually update it or develop the model. You need to start again from the start, from scratch, with a new and updated database or training data set. So that's the batch learning. So it's a bit difficult and complicated, because this one requires a large computational capacity as well as a large database on the get-go. And of course, once it's done and you want to change something, you need to start again. Now in the online learning, this one is, the training is incremental. So you feed the data on small batches. So basically it's the opposite one of the batch learning, whereas you can actually continuously improve your data as new training data are being obtained. So this is optimal for systems where data can change rapidly, so especially for the time series data, or if your hardware has a limited computational power that can only, of course, process small amounts of data at a time. Okay, so one parameter to remember about machine learning is the learning rate. So learning rate is the parameter that describes how fast the system adapts to your changing data. It's basically somewhat like attention span to us, to humans. Not the learning rate in humans, but more of the attention span. Because, for example, if you have a high learning rate, you have a very good attention. You're very attentive, so you can adapt quickly to new data. But because of high adaptability, and of course limited memory, you have the old data tends to be quickly forgotten. So high learning rate, too high learning rate tends to be more susceptible to noise, especially if the new incoming data are mostly outliers. So since it forgets the old established data, your model will tend to get biased to the outliers. And then we have the low learning rate. So this is in the low learning rate, it's less sensitive to noise and outliers, because it doesn't. The downside here is that it doesn't. Takes quite a while, several new data that must come in for it to actually adapt to the new data. However, this one is more resistant to the noise and outliers because it doesn't quickly forget the old data. So that's your learning rate. Okay, now we have several machine learning approaches to generalization or prediction. So in the usual application kasi, the usual application of machine learning is basically predictive. You want to predict whether the stock market, well, basically they're trying to predict the stock market movement based on machine learning. Or even you can try to predict the sales, end of the year sales based on the performance of the market, so on and so forth. Now, we have several approaches to this prediction. So we have the instance-based learning. So in this case, your machine learning or your system will create a prediction based on comparisons. This is the old data. So it's compared to this old data. This new data is most likely, based on this new data, for example, monthly sales. So you have, this is the performance of this month. So the expected sales output should be based from last 2 months ago's performance. It should be around this amount of sales. So that's the instance-based learning. So based on similarity on a previous known data. Now, in a model-based learning, it's a bit different. So in a model-based learning, it first creates a model. A holistic model. It's more holistic in approach. It creates first a model based on all of the past data. So it can be, say, a linear regression or even a regression curve. And it can create prediction. So, for example, this is the trend. For example, the sales trend in 2019 is that you have increasing sales as the months progress. You have this is, for example, your model is your sales output will be a factor of a combination of the month, the season or the month it is, and the performance of the market. So you have basically, say, performance of the market X plus the month it is Y. So you have basically a model, an equation. So using that model, then the next data. So for this month of April, say example, of 2020 or 2021, so the projected sales should be based on the model built from the past year's data. It should be so on. So that's model-based learning. So it doesn't use similarities, but rather it uses the model that was produced from the previous data. So those are machine learning. So if at the first look you have, it seems very good. It's like a panacea. So it's a cure-all for most of the problems that we have. But it's not really like that. So we have several challenges in machine learning. So first is insufficient quantity of training data. Because remember, your machine learning is only as good as the data you input it. Because you are teaching them based on the data that you are feeding it. So here, accuracy increases in proportion to the amount of training data. So an example of that here is a study testing the accuracy of several machine learning algorithms. And here you can see the pattern that rather, regardless of exactly what algorithm that you are using, it's basically not who has the best algorithm, but who has the most data. So as you increase the number of words, which is your data, you have increased accuracy. So you have basically the quantity of training data is important in machine learning. And then the issuance of a non-representative training data. So you have, for example, your training data is not representative of your actual data that you want to run it. For example, you want to know let's say, the stress levels of students in Mapua during online courses. And then your training data consists mostly of students from for example, CBMS department. So the school of CBMS. So these are the Chem students. So you check their level of stress. And then you try to apply it in the whole student population of Mapua. This is a non-representative training data because in the school of CBMS, there might be some differences or changes. For example, of course, you are not taking the same subject. You have specialized subjects that only School of Civil mistake that are not being taken by the other students, as well as the tendency of the faculty to give assignments, so on and so forth. So your training data cannot fully represent your population. So basically, this is in statistics. This is a sampling error. So you have a problem with your sample is not representative of your population. Okay, so we have several terms to consider. You have sampling noise. So if the sample, this is usually happens when the sample is too noise. Too small. And the sampling bias, if the sampling method is flawed. For example, again, you chose in your sampling method, you chose only the students that you know. And say if you are from the School of CBMS, of course, the people that you know tend to be mostly from the School of CBMS. So you have a bias in your training data. Okay, the next one is the poor quality of data. This happens, for example, missing data, missing information. What do you do with the missing information? Can you put zeros on all null or empty data in your data set? Of course not. For example, if it's a time series data, having a zero there it's basically putting an outlier there. So that's poor quality of data. Okay, so other things are having irrelevant features in the data. For example, the data is there's a lot of information in the data. That's why we have dimensionality reductions. So because we are trying to remove the features of the data that are not relevant to the model or to the problem that we are solving. And then we have the overfitting and underfitting. So overfitting is basically overgeneralization. So for example, in your class, for instance, so the students, my classmates, let's say if you have a classmates, for example, from the School of CBMS, my classmates are usually because how can I well, this is there's nothing not personal here, huh? Okay. So for example, from the School of CBMS, most of them are say girls, and they are usually a quiet bunch. Okay, so your classmates in the School of CBMS or the friends that you have that are from the School of CBMS are usually quiet and say very GC or grade conscious. So then you can tend to overgeneralize that. That means that all of the students in the School of CBMS are quiet and grade conscious, which is not really true. We have several different dynamics in the School of CBMS. But anyway, what I'm trying to say is you're trying to overgeneralize from just a small amount of training data. You are trying to overgeneralize. Basically, it's like you're being biased because of what you see. You are overgeneralizing it into the entire population. That's overfitting. The other one is the underfitting of the training data. This one is oversimplification. In the oversimplification, for example, let's say grades. The grades and student performance in the year 2019 and the year 2020. Because we can see that there's a very large difference in the performance. So an oversimplification of that is basically we can, if we just say that what's the main change from last year and from the last school year to this school year is that, well, the change to online learning. So you have we can oversimplify it. If it's an online learning, the students tend to perform very well. But this is an oversimplification because there are many reasons why the students always get a high score. It could be that it's easier to actually to cheat in, well, hopefully none of you are doing that, but it's easier to get around the rules if you are online or something like that. Or it's easier because you are using it's always open notes, the questions are easier. So that doesn't mean that the students perform better in an online setting, but rather the online setting provides the student easier way to that's actually another oversimplification for me. But again, just saying that the students perform better learn better in an online setting than in a face-to-face setting is an oversimplification of the data that you have based on the changes in the previous student performance of before the pandemic and in the pandemic period of the student performance. So that's oversimplification of the data, just because you are saying that you are creating a very simplified model that doesn't really represent the actual patterns that happens. That means there are many underlying complications, many underlying events that are being oversimplified and that are being ignored by oversimplification. So basically, this is underfitting. So basically, these are the challenges in machine learning. So that's it for now for machine learning. So in the next week, we will try actually doing a simple machine learning algorithms. Okay? So see you on next week.